Okay, so we have been looking at electroosmotic flow in presence of back pressure. We considered the Navier-Stokes equation and applying boundary condition we saw that we can obtain a solution by dividing the equation into two parts, where in the first part we will be talking about the electroosmotic flow, and the second part we will talk about pressure driven flow, and we will add the two solutions to obtain the solution for electroosmotic flow with back pressure. Okay. This is the situation we have been looking at. We have been looking at flow in a circular pipe, and where we have the walls have positive zeta potential, and the electric field is in this direction as you can see here. So we would expect the electroosmotic flow to occur from left to right, okay, in this direction, and the pressure gradient is positive in this direction. We have delta P here and P equal to 0 here. So the pressure driven flow is going to occur from right to left, okay. So and these two can be added together to obtain a solution for electroosmotic flow in presence of pressure drop. So we obtained a solution for the flow rate, okay. So the flow rate Q was Q electroosmotic plus Q pressure driven, and this is for ideal conditions. So ideal electroosmotic flow rate, okay. So we saw this is equal to pi S square U electroosmotic plus, sorry, this should be minus delta P divided by the hydraulic resistance, and we saw this as pi S square epsilon J divided by eta L into delta V. So delta V over L is the electric field, and epsilon J electric field over eta is the electroosmotic velocity, and pi S square is the area. So minus pi A4 over 8 eta L into delta P. 8 eta L over pi A4 is the hydraulic resistance. So we get an expression for the total flow rate, okay. So from here we can find out the pressure flow characteristics of the electroosmotic pump, okay. So what is called PQ characteristics. If you say that the zero flow, what is the maximum pressure that we are going to expect from the pump, and for zero back pressure what is the maximum flow rate that we will be expecting from a pump, and pumps are characterized by their pressure and flow characteristics, okay. So let us look at here. Now if we say the back pressure is 0, back pressure equal to 0. So this is the first condition. What is the electroosmotic flow rate, okay. So we can find in this equation, if you put the back pressure to be 0, okay, then let us say delta P is 0, we can find the flow rate, which is the maximum flow rate at 0 back pressure, is pi S square epsilon J over eta L into delta V. That is the maximum flow rate we can expect. Now we can similarly we can do for the electroosmotic pressure at 0 flow, okay. So now in this equation, if you put Q to be 0, okay, we can get an expression for the back pressure. So if you do that, if you put Q equal to 0, you can get the expression for the maximum electroosmotic pressure to be Q EO into R hydraulic, which is from here, okay. So this is the Q electroosmotic, and since this side is 0 into R hydraulic, okay. So we will get this as 8 epsilon into J divided by S square into delta V, okay. So what we see here, we see that the electroosmotic flow rate QEO depends on the electric field is directly proportional to electric field. So QEO is directly proportional to the electric field or delta V over L, and it is also directly proportional to the zeta potential and inversely proportional to the viscosity, and it varies as square of the channel size, okay. It varies as S square, whereas if you look at the back pressure PEO varies as 1 over S square, okay. So what we mean from here is, for in electroosmotic flow, if we increase the size of the channel, the electroosmotic flow rate is going to increase, but at the same time the back pressure, the pressure capability of the electroosmotic pump is going to reduce as 1 over S square. Whereas if you reduce the channel size, we will get very good pressure capability, okay. So it will increase as S square, but at the same time the flow is going to reduce, okay. So what we learn from here is that as A is reduced, the pressure capability is increased and the QEO is reduced, and as A is increased, the pressure capability is reduced but flow rate is increased, okay. So here we see the PQ characteristics plotted, okay. This is PEO, which is given by 8 epsilon J over S square into delta V, and this is the maximum flow rate, which is given by pi S square epsilon J over eta L into delta V, okay. And so this is the maximum flow rate when the pressure is 0, and this is the maximum pressure when flow is 0, okay. And the curve is given by this equation here. What we mean by when Q is 0, when you get maximum pressure, what we mean by is this, okay. So this is the situation where the net flow is 0, that means we have electroosmotic flow occurring close to the wall from left to right, at the same time the pressure driven flow is at the middle, which is from right to left. So the area, this area is going to be same as these two areas added together, okay. So then we would have net flow to be 0, right. Now if we take an example, let us consider an example, okay. Let us say zeta equal to 0.1 volt and A equal to 10 micron, okay, and so we have zeta potential 0.1 volt and the size of the channel is 10 micron, and the length of the channel as 100 micron, and the dynamic viscosity is 1 MPa. Then we can find QEO over V delta V is about 0.21 nanoliter per second per volt. Okay. And we can also find PEO over delta V will be equal to 5.52 Pascal per volt. Okay. So what we see here is the the flow rate and the pressure per unit volt unit potential difference is not much. Okay. So what we need to do is to use multiple channel pump. Okay. So in that case we can reduce the channel size so that we can get much better pressure capability. At the same time you can have multiple n number of such smaller channels in parallel, so that would give us n times the flow capability of a single channel electroosmotic pump. Okay. So this single channel electroosmotic pump do not have practical applications in microfluidics. For example, if you want to drive some fluid into a microfluidic device, such single channel electroosmotic micro pump may not be suitable, but these pumps may have some applications, for example in electrophoresis, where you want to carry some sample plug from one location to another, because one interesting observations from electroosmotic flow is that the profile is plug unlike parabolic. So there is no diffusion that occurs between different sections of the sample plug. So the sample plug is restored when it is transported from one location to another. Okay. And so if for some microfluidics applications we are interested in just transporting a sample plug from one location to another, we can use a single channel electroosmotic pump. Okay. But for many microfluidics applications we would need much higher pressure capability and much higher flow capability for the applications. Okay. So what we observe is that the single channel electroosmotic micropump used in free flow case, and the flat electroosmotic profile can be used to move concentration profile undisturbed along a channel. Okay. And as you know that the pressure capability goes up as the channel size goes down, but with channel size going down the electroosmotic flow goes down. Okay. So for that reason, if you are interested in decent flow rate, so electroosmotic micropump with decent flow rate can be constructed with large number of narrow channels in parallel. Okay. So you can have large number of narrow channels in parallel to construct the electroosmotic micropump, and that is called parallel electroosmotic micropump. So where we can consider n different microchannels, each having channel size of A and length L. Okay. So if you do that, we can say the Q electroosmotic for n channels is going to be n times the pressure capability of a single pump, okay, which equal to n into pi s square epsilon J divided by eta L into delta V, and the flow capability PEON is electroosmotic pressure, which is 8 epsilon J over A square into delta V. Okay. So what we see here is that the electroosmotic pressure will go up as A is going down. So we can obtain good pressure capability, okay, and so with increase in A, even if the electroosmotic flow rate for a single channel will go down, we can have many such channels in parallel. So using n different channels in parallel, we can also obtain good flow rate, okay. And it is possible to fabricate such large number of parallel channels using microfabrication technology, okay. So it is possible to obtain good pressure capability and good flow rate using electroosmotic micropumps, okay. Now such micropumps, if you want to increase the flow rate or increase the back pressure further, one approach to do that is increasing the voltage, okay. And for lab on chip applications, increase of voltage is limited, okay. We cannot keep on increasing the voltage to any extent. So one approach that could be followed is, if you can obtain good pressure and flow rate by without increasing the applied voltage significantly, and one such approach is known as cascade electroosmotic micropump, where we will have a net voltage drop 0 across one stage. At the same time, we should be able to obtain the required flow rate and pressure capability, okay. So let us say how we can do that. So what we see here is a cascade electroosmotic micropump. So we call it cascade electroosmotic micropump, okay. So we have a section of the channel, okay, part 1 and part 2. Part 1 has a size, channel size is A1, and part 2 has channel size A2, and we have the positive terminal at the intersection between two parts somewhere in the middle here. So this is positive, and the other two, this here the potential is 0, and here the potential is 0, and the potential here is some delta V, okay. So the electric field in part 2 is towards the right, as you can see here, and the electric field in part 1 is towards left, okay, as you can see here, and the pressure at the entrance of the channel is 0. Let us say here on the left hand side is pressure is 0. Let us say pressure at the right hand side where x equal to 2L, let us say the length of the channels are equal, this is L and part 2 is also L. So the pressure at x equal to 2L is delta P, let us say x starts from here, okay, and pressure at x equal to 0 is 0, pressure at x equal to 2L is delta P, and pressure at x equal to L is some pressure Pc, okay. So in that situation the net voltage drop going from x equal to 0 to x equal to L is going to be 0, okay. So in spite of having net 0 voltage drop across the stage, we can see how we will be able to generate pumping action, okay. So we see that the phi at x equal to 0 is 0 and we can see pressure at 0 equal to 0 is 0 and the phi at x equal to L is going to be delta V and P at x equal to L is some Pc, okay, and phi at x equal to 2L is going to be 0 and pressure at x equal to 2L equal to delta P, okay. So these are the boundary conditions and we apply that to this situation here where we have two channels in series and we have the potential difference as shown here, okay. So we can define something called a size ratio which is alpha and this is A1 over A2, okay. The size of the channel in part 1 divided by the size of the channel in part 2 is called size ratio. So you can define a parameter R hydraulic star which is 8 eta L divided by pi A2 4. So let us consider part 2 as the reference channel, okay. So part 2 if we consider as the reference channel, this considers part 2 as the reference channel, okay, and we can find Q EO star is pi A2 square epsilon j divided by eta L into delta V, okay, into delta V. So considering that, okay, considering part 2 as a reference channel, finding out hydraulic resistance, electroosmotic flow and knowing the size ratio alpha, we can write the flow rate, electroosmotic flow rate in part 1 of the channel is going to be alpha square into Q U star, okay. And similarly you can check Q EO 2 and this is going to be minus Q EO star, and this negative sign here is because of the direction of the voltage drop, okay, direction of voltage drop. So as I told, the zeta potential is positive, okay, zeta is positive. So the electroosmotic flow occurs in the direction opposite to that of the electric field. So in channel 2 electroosmotic flow occurs in this direction, in the negative x direction, and in the channel 1 the electroosmotic flow occurs in this direction, and that is the reason, since it occurs at negative x direction, we get a negative sign there, okay. So, R hydraulic 1, okay, the hydraulic resistance of the channel 1 can be written as alpha to the power minus 4 into R hydraulic star, and hydraulic resistance of channel 2 will be R hydraulic star. Okay. So, you can write this. Now, if you do mass conservation, we can see here, if you see here, we can see that since it is a continuous channel, two channels are in series, mass conservation has to be satisfied. Okay. If you say mass conservation, then you can write Q is QEO1 plus 0 minus PC divided by R hydraulic 1. Okay. So, the flow rate is going to be the flow rate due to electroosmotic flow plus that due to the pressure. Since the pressure is 0 here and PC there, we can accordingly find out what is the flow because of the pressure, okay, and this is the due to the electroosmotic flow. So, this is going to be alpha square Q EO star, as you can see from here, this will be minus alpha to the power 4 because the hydraulic resistance expression is here. So, that we substitute there. So, this will be minus alpha 4 into PC divided by R hydraulic star. Okay. So, this is one equation, equation 1. Now, the equation 2 you can write for the channel 2, which is Q equal to QEO2 plus PC minus delta P. So, this flow rate is what is coming from the left to the intersection of the channel, what is coming from here till this point, and then for the channel part 2 what we see, it has to be same as what is coming from here to there. Okay. So, if we calculate that, it comes PC minus delta P divided by R hydraulic 2, and which becomes minus QEO star, which we see it here, plus PC minus delta P divided by R hydraulic star. Okay. So, this becomes our second equation. Now, if you solve these two equations together, what we get is we get an expression for the central pressure PC is equal to 1 plus alpha square divided by 1 plus alpha to the power 4 into R hydraulic star and Q electroosmotic star plus 1 over 1 plus alpha to the power 4 into delta P. So, we get an expression for the central pressure. You can also obtain an expression for the flow rate. We can say Q is going to be alpha square minus alpha to the power 4 divided by 1 plus alpha to the power 4 into Q electroosmotic star minus alpha to the power 4 divided by 1 plus alpha to the power 4 into delta P over R hydraulic star. Okay. So, this is going to be the expression for the pressure and the flow. Now, from here we can obtain the expression for the 0 flow pressure capability and 0 pressure flow capability. So, from there we can find the 0 flow capability and 0 pressure flow capability. Okay. So, if you do that, if we in one case we put the back pressure to be 0 and the other case we put flow to be 0. If you do that, we can obtain the pressure capability PO at 0 flow is going to be 1 over alpha square minus 1 into R hydraulic star into Q electrostatic star, then and 0 pressure flow rate is going to be alpha square minus alpha 4 divided by 1 plus alpha 4 into Q U star. Okay. So, what we see here is that despite 0 voltage drop across a single stage, it nevertheless acts as an electrostatic pump. So, we have some pressure capability and we have some flow capability of the pump even if we have 0 net voltage drop across the pump. Okay. So, if you look at this expressions for the pressure capability and the flow capability carefully, what we see here is as alpha deviates from 1, we have larger electrostatic effect. Okay. So, it is very clearly seen if alpha is very small, okay, or it is very large, then the electrostatic pressure as well as the flow will be higher. Okay. And our special case would be when alpha equal to 1. So, for alpha equal to 1, if you put in these two equations, PEO will be 0 and QEO will be 0. So, we have no net pressure, okay, and no flow rate. Okay. So, when you say alpha equal to 1, what that means is that the two sections of the channel, part 1 and part 2, have equal size. So, in that case both produce electrostatic effect, but they are going to be equal and opposite. So, they cancel each other. As a result, we do not have a net pressure capability, we do not have any net flow that is occurring. Okay. So, now if you put alpha greater than 1, so alpha is A1 over A2, right. So, this is what is we have defined, alpha is A1 over A2. Okay. So, alpha is A1 over A2. As alpha greater than 1, that means A1 is much greater than A2. Okay. So, it says A1 greater than A2, then so in that case, if you in this equation, if you put alpha greater than 1, then you would see that the pressure as well as the flow that we get will be close to of that of the part 2. Okay. So, we say that the narrow part, that is part 2, narrow part 2 will dominate the electroosmotic flow. Okay. So, and the net flow, so you can see here in part 2 the net flow is in the negative x direction. Okay. The net flow is going to be in this direction. So, for alpha greater than 1, the net flow is going to be in the negative x direction. Okay. Now, if alpha is less than 1, so this is the situation when we are talking about that A1 is greater than A2. So, we have something like this. Okay. So, we have the A1 is large compared to A2. Okay. So, the net flow is going to be in this direction. Now, if alpha is less than 1, the narrow part 1 dominates the electroosmotic flow. Okay. So, we will have net flow in positive x direction. This is something you can observe from this equation. When alpha is very large, okay, when alpha is very large, this is going to be negative. So, the net electroosmotic flow is going to be in the negative x direction, and when alpha is less than 1, then we would have the Q electroosmotic to be positive. Okay. So, in this case electroosmotic will be negative. Okay. Now, we can have such 0 net voltage drop pumps in series. We can have many of these in series to build a micro pump which can enhance the pressure drop, okay, the pressure capability of a micro pump. So, that is called mini cascade electroosmotic pump, where we would have the channel 1 as many channel and channel 2 was single channel. Okay. So, this is shown here as you can see in the next page. So, as you can see here, we have many such 0 net voltage drop configurations in series. Okay. So, here is positive, then positive ground, positive ground, positive ground, and so on and so forth. So, you have net voltage drop across a stage is 0, but with that we will be able to generate electroosmotic pumping action, and we have many such stages in series, okay, to generate significant amount of the back pressure. At the same time, we have divided the part 1 of the channel into many channels, because if we divide them into many channels, for each of these small channels the back pressure is going to be significant, okay, and we have the channel 2, we have it is as a larger channel because we want also simultaneously larger flow rate. Okay. So, the idea is the channel 1 is divided into many small channels, and that is to obtain higher back pressure. Okay. And the channel 2, the dia is large to obtain higher flow rate. Okay. So, let us say we have divided the part 1 into n square channels. There are n square different parallel channels here. Okay. So, channel 1 has n square narrow channels. So, we say that A1 equal to A2 divided by n. Okay. So, the width of or the size of the channel in part 1 is 1 over n times the size of the channel in part 2. Okay. So, if we go back to our definition of the size ratio, alpha is A1 over A2, that is going to be 1 over n. Okay. Right. And we can say that the R hydraulic star is 8 eta L. R hydraulic star, the R hydraulic star is 8 eta L divided by pi a to 4, and Q electroosmotic star is going to be pi A2 square into epsilon into zeta delta V over eta L. Okay. So, the two parts have same cross sectional area. So, the cross sectional area A1 A2, okay, the two parts have same cross sectional area, two parts have same cross sectional area. So, A, so that is A1 equal to A2, let us say equal to some A. So, A equal to pi into A1 square into n square. So, we say that there are n square channels will be equal to pi A2 square, right. So, A1 equal to A2 divided by n, that is what we have considered here, okay, right. Now, we can define the hydraulic resistances Q U1 equal to 1 over n square into Q star, and Q UN for n different channels is going to be Q, okay. So, the subscript n, okay, subscript n refers to n square parallel channels, okay, and Q EO2 is going to be minus Q EO star, okay. Similarly, we can obtain the expression for the hydraulic resistance R hydraulic 1 is going to be N4 into R hydraulic star, and R hydraulic N is going to be N square R hydraulic star, and R hydraulic 2 is going to be R hydraulic star. Okay. So, we have defined the flow rates and the hydraulic resistances in the one small narrow channel, also n different narrow channels, as well as in channel 2. Okay. So, with these definitions, what we are going to do is we are going to write the expression for the conservation of mass, where we equate the flow rates in the part 1 and part 2 of the channels, and by equating the flow rates we are going to obtain an expression for the pressure and flow rate. Okay. So, we will continue that. So, with that let us stop here.